A confirmation about the audio, please, if the audio is clear and available. Thank you. Till now, the portion that we are covering, is it consumable? Is it something that you're finding it that, okay, you will be able to understand that? Or any of those areas that you're finding it very incorrigible, something that you think that it is simply out of the world? Please do let me know about that as well. Is it understandable? Is it consumable up till now? Okay, good. Here also understand, guys, that as of now, many of you would be confronting many of these concepts for the first time. Many of you would be taking a look at these particular concepts for the first time. So the ideal approach should be not to try to learn immediately in your first reading. That is the absolute wrong approach. Okay, many of the candidates you will see even in your surrounding, I don't know if you do the same process or not. In case you also follow the same process, then listen to this very carefully. Many of the times as candidates for civil services, we basically are aware that, okay, these are the books that we have to study, and our approach is that we will ratify these books, we will get to the civil services. But it is not a sprint race that you are running. It is not a 100-meter race that you are running for. It is a marathon that you are going to struggle for. So always advisable, not only for the subject of geography, but for all the various subjects, that the first reading that you carry out, that should be in a way of explorative medium. That should be the way in which you familiarize yourself to the concepts. You become familiar with the fact that, okay, there is indeed something referred to as the plates. Okay, so these plates, when they move, that is why the Himalayas that we see, that is why they are created. Now chances are that when you follow this approach, in the after the first reading, there will be certain loopholes in your concept here and there, and that is why periodic revision comes into the place. Still, at the end of the entirety of the modules, when you go for the first reading, it should be on a familiarization basis. That are you getting more and more familiar with those concepts, or is there an issue thereby? Once you become familiar with the concepts, then comes the role of the second reading or the role of the revision. And that is when those concepts are grasped in greater detail. Examples that will start sticking in your mind. But still, many of the classifications is something that will escape your mind. And that is when the third phase of revision comes in. So, only and not only for the subject of geography, let me make it absolutely very, very clear. It goes true, it holds true for almost all the subjects that you read. You would also have found it from your own experience that the first reading that you carry out for polity or for history, that is much more for a familiarization. You won't be able to solve many multiple choice questions at the end of it, but you will get an idea, okay, what fundamental rights they deal with, roughly these concepts. And that should be the approach I want you to follow. Only after the second reading should you go for underlining of those important concepts, note making, etc. That should come after second reading. That is when efficiency is gained. Okay. Now, Zabir, why denser the material, higher the velocity of seismic waves? That is because, see, when the materials, they are very closely packed to each other, any variation in the first material will immediately impact the second one. That will immediately impact the third one. And that is the case with solids. That is the case with higher density. Higher density means what? Particles are much closer to each other. When we talk about lower density, so there is a distance between the particles. So let's suppose there's a disturbance in the first particle. It will take some time for that disturbance to be propagated into the second particle. It will take some time for that disturbance to be propagated into the third particle, and so on. So that is why it takes longer period of time to get transmitted in materials of lower density. But when the particles are very closely packed, it will immediately be transmittable. Okay. Sia, is there any technical glitches? No, not from our ends. But I hope the audio and video is working fine for everyone. Any issue thereby, please let me know. Okay, it is working fine. Good. So those who facing any issue, kindly try to refresh it. Okay, try to refresh it. So now we move ahead, we proceed ahead with this, and we talk about the types of volcanic landforms. So this classification in types of volcanic landforms that we talk about, this is basically whenever there is an eruption. Now it ends up creating various different types of landforms in the sense that from the central vent, let's suppose there's an eruption. How can we get the answers corrected? Send your written answers immediately to IS Live or Target IS. We have a very good empaneled list of evaluators, and we ensure that whosoever we enroll as evaluator, they do have certain amount of mains examination that they have qualified, not only appearing for the mains examination but qualified few of the mains examination. Only those guys we pick up as the evaluators, because they have some experience about the type of questions and the type of answers required. So those evaluators basically will go through your answers in significant detail. In certain cases, we also go through your answer sheets, and then we get an idea about how you we will give you the feedback, we will give you the comments required, and accordingly you can improve. Okay, so Target IS or IS Live, please immediately send it over. Now, let's suppose there's a volcanic vent here. Okay. And through that volcanic vent, there is magmatic material which comes out. Now, magmatic material can be very sticky, can be viscous, can be fluid. It can be of various types. Now, sometimes it will happen that the magmatic materials, they accumulate very close by. Sometimes it will happen that the magmatic materials, they spread over very large distances. Sometimes it can also happen that if there is a vent here, let's suppose, now you will find that the materials, they basically end up forming a kind of a solidified portion just like this. So like that, you have a variety of different landforms which are created as a result of volcanic eruption. So you have, based upon that classification, cinder cone, composite volcano, shield volcano, as well as the lava domes. So we will take a look at each one of them separately. We'll try to understand where do they get created and what are these landforms exactly that we are talking about in terms of their shape. Okay. We did not solve PYQ last few hours. In the initiation of the class itself, we handled one of the PYQ dealing with the topic. So slowly and steadily, we'll take it up. Don't worry. The portion of geomorphology is much more important for your mains examination. It is this year that UPSC surprised the candidates by putting a question of geomorphology in the prelims. But if you have been regular in the class, if you have followed the class, even those questions are easy to solve. In climatology, you will find many of the prelims based questions. Okay. So one by one, let us take a look at it, that what are cinder cones, what are composite volcanoes, what are shield volcanoes, and what are lava domes. So when we say cinder, cinder is associated with the burning fire of sorts. So for example, when you burn wood, etc., you would have observed the small cinders of wood burning, right? So when you have some type of volcanic eruption, whenever you think about a volcano, the image that is created in your mind is kind of a what? The image which is created is of a simple landform which is conical in shape, right? Where you have molten materials which are expelled, which are erupted, and those molten materials, they settle down across the slopes and they then solidify, right? So that is cinder cone. Let us take a look at them. So basically, whenever you talk about cinder cones, they occur when particles and blobs of lava, that is chunks, blob refers to chunks. So chunks of lava, they are ejected from a volcanic vent. Lava is blown violently into the air. Generally, this involves a kind of an explosive eruption. Explosive eruption. Okay, so the lava is blown violently into the air, and the pieces, they start raining down around the vent. They start accumulating around the central portion of the vent. So that is a cinder cone. Why the name cone is associated? Because that is the shape that they will take. That is the shape that they will form immediately after the eruption. Because from the central point here, as the materials are expelled, now all those materials, when they move up, they are thrown up with some amount of pressure, some amount of force. They will all start accumulating around the portion of explosion, of the eruption. And that is how eventually you will observe the formation of a kind of a conical structure thereby. Okay, a kind of a conical structure is created. So that is what we refer to as a case of a cinder cone. Generally, they are not very great in height. 1,000, 1,200, 1,500 feet is the maximum height till which they will go, not beyond that. Now, over time, this builds up circular or oval shaped cone with a bowl shaped crater at top. There will be a bowl shaped crater of sorts, where you will have, in many of the cases, the molten materials. In certain cases, the molten materials would have solidified, and that forms the portion within the crater. Now, in this situation, after, let's say, the volcanic eruption has occurred, then all the molten materials which were present, they will also start solidifying. In the region of the central vent itself, they will also start solidifying, and they will form the solid plug. Okay, around the vent, they will basically solidify, form the igneous rocks. So for the next time that the eruption has to occur, next time when the eruption has to occur, the molten materials and the gases, they have to blow through, they have to blast through all this solidified igneous rock. So think about it. Whenever you need that requirement of that blasting through these solidified rocks, it will require an explosion. It will require an explosive eruption, right? So that is what the cinder cone is associated with. Height in general is around 1,000 feet. That is it. Not very great in terms of height. Okay, not very high. Example: Mount Tal, Philippines. Okay, that is an example of cinder cone. Across many of the larger volcanoes, also you will find small cinder cones getting created on the sides. So these basically give you an idea that molten materials have basically broken through the surface, accumulated in the surrounding, and you have the formation of these cinder cones. Then comes the composite volcanoes. Composite volcanoes are amongst the largest landforms created due to, amongst, not the largest, amongst the larger landforms created due to volcanic eruption. These are also what are referred to as stratovolcanoes. And when we say strato is derived from the term strata, and strata always refers to the existence or the presence of layers, right? So whenever you have certain kind of volcanic eruption, some amount of volcanic eruption, it is not always going to be the case that you will have same kind of materials which are emitted or which are expelled every time. You can have different types of materials of different density, of different magmatic makeup, that make up these particular eruptions. Generally, across convergent boundaries, you will find these kinds of eruptions taking place. So here, stratovolcanoes refers to existence of various different layers in terms of the deposits that you see. Existence of layers and various different types of layers. So a simple example of this, that how this can get created, let's suppose this is the central volcanic vent here. Let's suppose. Now from this portion, materials, if they are thrown out, That is the magmatic materials if they are thrown out here. So when you have these magmatic materials which are thrown out, now let's suppose that magma settles around in this portion, solidifies, lava solidifies and forms this particular area. Now after that, during an eruption, lot of ash is also released, lot of various different other materials are also released. So let's assume that after some time you have a deposit in terms of ash that also gets solidified over a period of time. Okay, now again, let's suppose after a few years, after a few decades, let's assume there is another eruption, and that means lava will again spread over. It can spread over a large distance and again it will solidify. So what are you observing here is basically a formation of a layered kind of a structure. Obviously, when you have this kind of a layered structure, now think about it. Ideally, only if the ash would have settled, that ash could have been removed by the various forms of erosion, etc. But again, another volcanic eruption means that ash is then trapped in between those layers. So when you have such consecutive layer formation which happens, which takes place, that means the size of the landform will be considerably larger. So that is where it creates a layered form of multiple deposits of ash, lava, solidified lava, pyroclastic materials, and so on. And that creates a larger structure thereby. So that is a composite volcano or a stratovolcano. Example, Mount Fuji, Japan. Very good, Pavni. Example, you have Mount Fuji in Japan. Right? That is an example of this. Mount Vesuvius is also an example of this. So these are basically your examples of composite form of volcanic eruption. Then you have one of the largest again, that is the shield. Now shield, basically the name is taken from the weapon system, that the shields that were used earlier in the battlefield. Now they used to be a kind of a flat featureless structure. The shield, whenever you think about it, it is a kind of a almost flattish simple structure, featureless structure. So when you have very fluid lava which can flow almost like water, very fluid lava. Now that fluid lava, it can spread over. It does not require, won't be able to accumulate itself in a particular region. So as soon as it emerges out of the central vent, it will spread over like a flood, right? So it spreads over a very large distance and then solidifies. And that is what is referred to as shield volcanoes. It is one of the largest volcanic landforms which are created. So here, basically created due to fluid lava flows, generally basaltic in nature. Generally basaltic lava flow. Okay. Now it will flow so very easily that it will spread itself over a very large distance. For example, if you consider the regions of the active volcano across the world, that is in the region of Hawaii, you have Mauna Kea, that is one of the examples of the shield volcano. Then you also have the case of the Canadian shield, the Deccan traps in India. All these are examples of shield volcano. Okay, so example here, you can take off Canadian shield, Mauna Kea, Deccan Traps, Mauna Loa as well. Yes, that is correct. So these are basically examples where you will observe a kind of a structure which is almost plain, flat, and featureless. Okay. Now they have very gentle slopes and are developed horizontally. Please understand that here the material which is coming out is fluid. Now, for the fluid materials to come out, will you need an explosion for the materials to come out? No, it is generally for the sticky materials which don't flow easily. It is for that you require an explosive eruption. So generally this is associated with a non-explosive eruption or an effusive eruption. Associated with a non-explosive or effusive eruption. That is what gives rise to the presence and the formation of these shield volcanoes. So they are developed horizontally. The horizontal expansion takes place. They are built by effusive eruptions which flow out in all different directions because the lava is very fluidic. Now, then you have the lava domes. Now, in the case of the lava domes, what happens is that material is very, very viscous. It doesn't flow easily. Now, here I want you to associate with the normal liquids that you see around you. Now, all the liquids, they don't behave the same way. They don't flow in the same way. You do have the presence of certain liquid materials such as water, which will flow easily. And you also have certain liquid materials such as honey, which doesn't flow very easily, isn't it? So, when you have such materials which are very sticky, viscous, now in that case, if you have, let's suppose, the presence of the volcanic central vent. Now the materials, they come out, they solidify here. Okay, they start solidifying here. And they solidify. This is the structure that you observe. So obviously not at all great in height. Now for the future eruptions to happen, materials again will come out and basically the size will increase from inside. As the materials tend to solidify, the size will increase from inside, right? It will start growing larger, slightly larger in size, but then again, the extent at which it will, or the extent to which its size will increase, that is also absolutely limited. So here, lava domes form when viscous means doesn't flow easily. Viscous means does not flow easily. Okay, it basically ends up being sticky in nature, accumulates around a vent. It starts accumulating around the volcanic vent. It can be symmetrical, while mostly they are irregular in shape. Now they grow. Fresh eruptions make them grow from inside. Okay, imagine just like a balloon. If you inflate a balloon, how it slowly and steadily expands, similarly the lava dome also starts expanding. Example, lava domes of St. Helens in North America. That is an example of this. Now, before proceeding ahead, why lava viscous in this? So it is not only that only in lava, see, understand, lava which is created or the magma which is created, depending upon the material presence, whether it is rich in silica, whether it is rich in iron, magnesium, that determines whether it will be viscous or whether it will be fluid. If it is fluid, then it will form the kind of a shield volcano. If let's suppose it is very viscous, it will lead to these kinds of. So here, depending upon what is the presence of material in the interior around that area where the eruption is happening, what are the molten materials present, what is the mineral distribution present, accordingly you have the different kinds of landforms which get created in the process. Okay, Ganesh, I hope that is understood. Okay, now if lava gets cooled, then how can it grow from inside? So imagine a situation, if this is connected to the volcanic vent from inside and you have viscous sticky materials which are trying to come out, so how will they come out? They will start solidifying as they come out. So as they start solidifying as they come out, the existing surface, won't it be pushed slightly outwards? So that is why it basically expands from inside, in the sense that newer materials will start cooling in and the existent materials, they will simply start expanding. They will rupture as well in many of the places. They will crack, they will break in many of the places, and newer materials will start occupying that region. Okay? Is that understood? And Priya, if it stops erupting for some time and then erupts after some time, then the process will be same growing from inside. Yes, generally. In most of the cases, you will find that that is what I was saying. That let's suppose it has erupted, and after that, re-eruption happens after, let's suppose, 50 years. Now, in that 50 years, this portion would have solidified quite sufficiently. It would have become solid, hard rock. Now, in that case, for the fresh eruption to happen, so it will either blast off the surface. If it has got enough pressure, it can blast off the surface. But generally what happens is that as the newer molten materials, they start coming over, due to the high temperature, some of these rocks also present in the interior, they also start getting converted into a kind of a semi-solid state. And that is where the expansion happens. Now, when that expansion happens, whenever any solid substance it tries to expand, then there will be cracks which will develop. And wherever the cracks will develop, the molten material will try to emerge out, it will solidify that crack. And that is how eventually, after, let's say, again 20 years, when you take a look at it, lava dome will be much larger in size. Okay? Niranjan, what is the difference between caldera and a crater? What is a caldera, my dear friend Niranjan? Please enlighten the class, because the class has not covered caldera. I'm sure you have covered caldera. That is why you have asked this question. So what is a caldera, my dear friend? You tell me that, I will tell you the difference between a caldera and a crater. Otherwise, kindly wait. When we cover caldera, this would automatically be understood. Okay? Smart people are good, but sometimes when we become very, very smart, that also creates an issue sometimes. Have some patience, my dear friends. We will cover all the portions. Now, here, before moving ahead, another concept I want you to introduce, yourself to introduce to, that is the portion of parasitic cones. What do we understand by parasitic cones? So many of the times what happens is that when you have a creation of a very, very large volcanic landform, very large volcanic landform. Now, over a period of time, this central portion that you see, the vent, that vent would also have been solidified. It can happen that the vent would have solidified quite significantly. Now, solidified means we are talking about hard igneous rocks in this case, right? So they would have gotten solidified in the process. Now, here, for many of the cases, the molten materials, they find it incredibly tough to break through these solidified portions. They find it almost impossible to break through maybe 1,000 feet or 1,500 feet worth of these solidified igneous rocks. But the molten materials, they have got pressure, but maybe not enough pressure to break through this. So what they do, they start moving through the weaker portion. Wherever in the entire landform which has been created, obviously there would be weaker areas, weaker cracks, etc., which would be in existence. So they start moving through the weaker portion. Now, if the weaker portion is where they have come through, now they are getting supplied from the same magma chamber. But they have, rather than being able to break through the central vent, they have found a new passageway. And the magmatic materials or the lava erupts. Now, this is a kind of a cone which will get created based upon the same magma chamber, but not across the central vent, somewhere else. So, that is what is referred to as a kind of a parasitic cone. So, this is what is also referred to as a parasitic cone. Okay, so parasitic cone is where you have the supply from the same particular magma chamber, but basically it is not the central vent, it is on the side. That is a parasitic cones, right? Yes, just like the secondary pipes in a way. Okay, like a predator band prey parasitic cone. Okay, so basically it is from the same source, but unable to break through the central vent, so somewhere on the side. Okay, so this is the case. So in majority of these stratovolcanoes, you will find multiple parasitic cones on the sides. These parasitic cones, they won't gain greater height, because after some time even this portion will get solidified, so they will find another weaker portion to erupt through. So they are not going to have very great height, supplied from the same magma chamber. From same magma chamber. Okay. Uh, After I asked the question, I got internet problem, didn't get the answer. And your question was that if it stops erupting after some time, then erupts after some time. Okay, so your question was about the lava dome. So understand this carefully. See, once you have the lava dome, let's suppose the viscous materials, they have solidified immediately. If this is the vent, now immediately above it they have solidified here. Now, let's suppose they have cooled down, solidified, and another eruption happens after 60 years, 70 years. 70 years is a long time for this entire formation to have a very solid igneous rock formation. Now, after 70 years, if again some viscous material is trying to come out, now there can be only two possibilities. If there is so much amount of pressure in those molten materials, it can break through the surface, it can disintegrate the surface and form a violent explosion. But normally that is not the case, especially in the case of lava domes, because the materials are so very viscous that these materials, they will start accumulating here in the interior. Now, these are molten materials that we are talking about. They will start accumulating, they will start pushing the existing portion. Now, the existing solid rock, when they are getting pushed from all sides, they will develop cracks. Also understand that the molten materials are at a much higher temperature. So some portion of the solidified rocks, they will get converted into semi-solid or a plasticky state where it can be deformed. Now, either that will lead to the expansion, but nonetheless, the solid substances like rocks, when they are suddenly asked to expand, they will develop cracks in between. And in those cracks, the molten materials will patch up those cracks, and together they will solidify as a larger lava dome. Again, let's suppose it has solidified. Again, after 100 years, again there is another eruption. So again, the same process. The molten materials, they will soften the underbelly of it. It will be pushed from all sides. As it is getting pushed from all sides, some openings will emerge. In that, the molten materials will fill up those openings. They will again create a larger lava dome. That is what we refer to as expanding from inside. Is that understood now? If the volcano blast, its lava doesn't travel far. Yes, generally the explosive eruptions, you won't find very far away moving lava domes. Um, Kumari, is the lava may not solidified in inside? In which particular case, my dear friend? Is it the case of lava domes? So yes, sometimes it does solidify, sometimes it might be possible that it is in a molten state for a long time. But generally, after some time, when it loses its energy, the entire vent, that will indicate a kind of a solidified portion. That is what we refer to as a lava plug. Okay. Yes. Drishti, St. Helens is in North America. Okay. Lava domes can be compared with gum bottle for yes, something like that. Yes. Is that understood now? Okay. So now we move ahead with another kind of volcanic landform that we observed, that we studied during the plate tectonics when we were studying about the divergent plate boundaries. If you recall, we had studied about the fissure volcanoes. What are these fissure volcanoes? So fissure basically refers to a crack. Okay, a large crack, that is what is indicated by a fissure. So sometimes what you observe is that across the earth's surface, across the land area, there is development and formation of very large cracks. Very, very large cracks. Right? The image that you see on your screen, observe this. You will observe the creation of a crack all the way from here to here. Now, molten materials, they start erupting out of these cracks from various different places. They will start erupting and emerging out of these cracks at various different places. Now, as the eruption is happening all across this region of a crack, this is what, or all across this fissure, this is what is also referred to as a fissure volcano, generally observed across divergent plate boundaries. Generally observed across divergent boundaries. Example, Laki eruption in Iceland. So, Laki eruption, as we have already talked about, that Laki eruption which erupted, or the eruption happened in the 1770s, it continued for almost 10 years. That eruption slowly and steadily continued to expel lava from inside. And why did it occur in Iceland itself? That is because, as we have seen, that Iceland lies bang in the center of the North American and the Eurasian plate, that division, right? So that is why, as the land was moving away, as the land was drifting away, you had these fissure created, where over a span of multiple years from that point of time, you had frequent volcanic eruptions, expulsion of lava, which solidified into newer crustal areas. Okay, so generally observed across the divergent boundaries, and hence this is also what is referred to as Icelandic form of eruption. Icelandic form of eruption. So the name which is given to the eruption type is also based upon where you will observe that happening very frequently. For example, when we talk about the shield volcanoes, these are also what are referred to as Hawaiian type of eruption. These are also known as Hawaiian type of eruption because that is something which is observed and noticed in Hawaii. Eruption. So even in the classification of volcanoes, you have classification in the form of how the eruption also takes place. So for example, you have Strombolian, Pelian, and so on. You have many different volcanic, you have many different type of eruption based upon where it is observed. Okay, so that is something not required for your general studies, so we'll not go into the depth of that. So fissure volcano, observe here that you have these large fissures which get created, through which molten materials, they spread out. So they are formed due to slow upwelling of low viscous magma along a long fracture and fissure. The resultant lava is spread over the ground surface quite significantly. It is known as Icelandic type of eruption because it is frequented in that area. Any doubts that we have till now? Is that absolutely clear? Perfect. If lava is formed and erupted, then what fills the volume decrease in the Earth's interior? Fresh lava gets created. And where does the fresh lava get created? So every time, every moment, you will have some or the other portion of the crust getting subducted underneath the crustal portion due to convergence. Right. So there is a continuous recirculation of the crustal layer which happens where the older crust it undergoes subduction, it melts, enriches the region of the molten area, it further forms lava or magmatic materials in certain areas, and it again rises up. So it is a continuous process. Okay. Why it's not form a mountain? Which particular mountain, Ganesh? When we talk about the volcanic eruption, in many of the areas, it has created the mountains. Multiple different eruptions. For example, take the case of Mount Cotopaxi. Mount Cotopaxi, what you see in Ecuador, which is situated very close to the equator, it is one of those volcanic eruptions which has created a mountain out of it. Mount Kilimanjaro in Africa, the highest peak of Africa, it has a volcanic origin to it. When you talk about Mount Aconcagua in South America has got a volcanic origin associated with it. So all the mountains, Mount Pinatubo in Philippines, Mount Fuji in Japan, all these are mountains which get created. Okay. Then the crust will become thin. No, absolutely not. Crust, the thickness of the crust is not dependent upon the fact that if you have volcanic eruptions in a region. See, crust continuously, you have to understand the process of recirculation, what we talked about, that here, let's suppose this is the crustal layer which undergoes subduction. Now, why does it undergo subduction? Because there is a convection current somewhere, isn't it? Wherever there is a convection current, there will be creation of a new crust in the process, and the older crust gets subducted. It is this crust which will form the molten materials which will rise up and form these landforms, isn't it? So it is a continuous process of balance. Why fissure volcanoes are in the form of a box structure? Where do you see a box structure? Fissure volcanoes here. This is the example of this is the image of a fissure volcano. Don't get confused by the graphic image of that. This is the example of a fissure volcano. Okay. I want you to observe carefully these particular landforms. Observe these landforms. All these have been created because of solidification of lava. So across the crack, wherever the eruption has been happening, it will form that. As the lava spreads, lava can spread to any particular region, to any particular length, depending upon the fluidity of lava flow as well. Right? So that basically determines the flow pattern of it. Okay? Will it create extensive black soil? Not all the volcanic landforms create extensive black soil. Most of them will create red soil. But when you have the basaltic lava, the flood basalt lava as it is referred to, that will form the black soil. Okay. Puja, slow upwelling of lava. In which particular portion are we talking about, Puja, here? And Srimant, how will we differentiate mountain from conversion and from lava eruption? Both from common man are same. So for the common man, hills are also the same. Generally, when you take a look at any particular hill or a mountain, unless and until you analyze the rocks, you won't be able to distinguish whether it is a fold or whether it is created out of volcanic origin. Many of the times, you have the volcanic eruptions or the volcanic mountains embedded within the fold as well. In the Andes, for example, you will have the presence of the fold as well as the volcanic eruption which gets created. So there is not much to distinguish. Generally, in the case of a fold, you will observe a presence of a conical peak. Whereas in the case of a volcanic mountain, you will observe a broader, flattish, sometimes a depression of sorts or a crater of sorts. But then again, that is something which, after a point of time, as the erosion and events of wind and outside nature takes over, even that difference is taken over. For example, Aravallis that you have in India, they are amongst the oldest fold mountains across the world, created easily billion years back. Now, in those Aravallis, you also have the evidences of volcanic eruptions. But right now, you won't be able to distinguish the volcanic mountain from or the volcanic hill of the Aravalli from the other hill, because the unless and until you analyze the rocks, you won't be able to distinguish in many of the cases. And Abhishek, fissure volcanoes are always going to happen due to divergent of plate boundaries. Most of the cases, in majority of the cases, in certain cases, transforms can also create, but in majority of the cases, it is going to be divergent. Okay. So now we move ahead to the portion of calderas. Calderas are different from the normal general volcanic landforms that we have seen till now. Calderas, they get created due to a series of circumstances which should have been present and which needs to be present for, and series of certain particular conditions need to be met for the formation of a caldera. Now, before we take a look into how the process of formation takes place, I want you to think about something and apply your logic as we talk about a process, whether that stands true on a logical standpoint or not. So here, let's suppose you have a volcanic landform in this area. Let's suppose. Okay. Joined by a central vent. Now, this vent is then joined to the magma chamber. This is your magma chamber. And listen to this carefully for the next couple of minutes. Now, here, let's suppose that the magma chamber is almost empty, right? And before emptying out, it is one of the final eruptions which is taking place. Now, that magma chamber can get recharged again very quickly. It is not as if once the magma chamber is empty, it is empty forever. It can get recharged again. But let's suppose in the final phases, when the magma chamber is almost empty, you have a lot of gases, some of the molten materials which are present. Okay. And there is the very explosive eruption which takes place. Very explosive. Now, whenever you have an explosive eruption, now, due to the strength of that explosion, due to the impact of that explosion, the existing landform might develop cracks here. Due to the impact of the eruption, the existing landform might develop a kind of a crack in this place. Okay. Now, that crack has been induced. Why? Because of the strength of explosion. Which explosion? As the magma chamber is trying to empty itself, that explosion. Now, after some time, when that explosion has happened, when that eruption has happened, materials, they have forced their way to the through the central vent to erupt out. Now, the magma chamber is empty, isn't it? Now, the magma chamber, let's suppose after the eruption, you have the development of the crack, and the magma chamber then becomes empty. Then what? Then we have a kind of a vacant space underground. And on that vacant space, you have all that weight which is imposed on top. So when you have a lot of weight and underground the region is vacant, what happens? The region will subside. It will simply settle over, isn't it? It will cave in of sorts. So the upper portion above the crack, wherever the crack was developed, that upper portion simply caves in. Right? It sinks because the magma chamber has now become empty. So as it sinks in, so you are left with a kind of a remnant of sorts. You are left with a kind of a remnant. Now that remnant which is left over, where earlier it was a part of a major volcanic landform, but then that landform has sunk, it has subsided because of the vacant magma chamber which could not withstand the entirety of the weight. That is when you have the formation or the creation of what we refer to as a caldera. Mostly this occurs when the eruption is very explosive, and the very explosive eruption will always occur closer to the water bodies. Closer to the water bodies, the amount of eruption, the eruption becomes very explosive. Now I will slightly go into the area of optional for a brief moment. Please don't mind it. This will improve your understanding as well. So many of the times what happens is that when you have the presence of seawater around that region has got a different pH value. Now seawater, if it starts percolating through, we are talking about why closer to the ocean or closer to the water body, it becomes very explosive. Now that seawater, if it manages to percolate through, it gets in contact with the molten materials and high temperature. Seawater immediately will start vaporizing. All that excess vapor will start accumulating, right? So you have the buildup of gases, lot of gases will build up, and that will bring about a kind of an eruption which is very explosive. So whenever water comes in contact with the molten material, that brings about a new phase of explosiveness, a new level of explosiveness. And it is in that high amount of explosion where the existing landform, the existing mountainous system, that will develop a crack. Now, the magma chamber has also emptied itself, so it won't be able to withstand the entire weight. That is why the central portion caves in. And generally, seawater from surrounding will enter into this area. It will form a kind of a larger pool of water in between, and that is what you refer to as a caldera. So how is a caldera created? So basically this example, this image that you see is that of a caldera lake. Now imagine at one point of time in history, this would have been a kind of a larger volcanic mountain of sorts, but the central portion has simply sunk in. So generally formed, generally created in the final stages of eruption as the magma chamber empties itself. Now, a very explosive eruption builds cracks in the existing structure, volcanic landform. Then the emptied magma chamber is unable to withstand the weight above. They are not able to withstand the huge weight imposed from above. So that is why the central portion around those cracks, they simply cave in. So that is why the central portion around the cracks caves in. Just a moment, guys. The central portion caves in. Then water from the surrounding areas from the surrounding regions fill in the depression, forming large calderas. Okay. So example of this, for example, when you had the very explosive Tonga eruption, which occurred in January of 2022. Now, that was amongst the most explosive eruption occurring in recent past. Now, the Tonga eruption occurred in South Pacific. I hope that you would have heard about the Tonga eruption in January 22. So basically, that occurred in southern part of the Pacific, but the impact of it could be felt in India as well. And the shock waves traveled through the entirety of the planet twice. The amount of smoke which was released, that traveled up into the atmosphere for almost 100 kilometers from the surface. So that created a caldera. Okay, so you have many such calderas. For example, even the Krakatau eruption in the region of western portion of Indonesia, that also created a caldera. You have, for example, Crete in Greece, that is also an example of caldera. So you will find multiple such calderas in existence. All of them are a resultant or an outcome of such explosive eruptions. Okay, now that water is in fluid form or in liquid form? Fluid and liquid, I was under the assumption they are same, but then it is in liquid form. But then when you are talking about the percolation of the seawater going into the lower region, that basically is in liquid form, and then when it gets in contact with that magma, it immediately gets converted into steam, and that blasts through the surface with incredible amount of power, right? And in Aravali Hills, what is the cause of lakes and other rainfall which gets accumulated in that area? That is it. Is this water poisonous? No. There is no choice to form lava in magma chamber after the formation of calderas. No, it can get created. If let's suppose there's a convergence nearby, it can get created. Lonar Lake in Maharashtra, where water turned pink last year. Lonar Lake is not a volcanic landform. Lonar Lake is not a volcanic lake. Lonar Lake is created. Why? Let me see if we are aware. How is it that the Lonar Lake has been created? Are we aware of that? And why is it that we regard Lonar Lake as so special? Very good. It is because of the meteorite. meteorite collision which happened. And why Lonar Lake is considered to be a kind of a geo heritage site is because this is one of the only places on the planet where we still have the evidence of the meteor hit on the basaltic rock, right? Where the evidence around the Lonar Lake, you have the basaltic rock, and that basaltic rock generally constitutes our ocean bottoms. So the impact created on the basaltic rock by the celestial collision, that is what makes Lonar Lake special. And the pink color that happened was because of the development of a species of bacterium out there. Okay. No, it's okay, Sridevi. Absolutely okay. In water have so many minerals in it. Yes. Okay. So that is basically the creation of calderas. Glacial lake outburst flood. That is a different thing altogether, my dear friend. That is something that you find in the Himalayan region. Okay. Is this portion understood about calderas? That how the calderas are created? Very quickly, I'll recap it. Generally, when the magma chamber starts turning empty, sometimes you have the presence of the nearby water bodies, such as oceans and seas, we are talking about here. So that water starts percolating. Sometimes even groundwater can do the same purpose. When it gets in contact with these, then huge amount of steam and vapor gets created, and that huge amount of steam and vapor, that simply tries to burst through with incredible amount of force, with incredible amount of pressure, and that basically turns into a very violent explosive eruption. That violent explosive eruption leads to generation of large cracks in the mountainous structure. In the meanwhile, the magma chamber has been emptied. So there is nothing there. It is a vacant space, and it is unable to hold the weight of the imposing structure on top of it. So due to that, the top structure simply capsizes, it collapses, it caves in, and the nearby water bodies such as the seas, etc., they enter into that area and they form a larger lake or a water body. For example, in the case of Tonga, you had two particular Tonga eruption and the Tonga Islands, you had two particular volcanic vents and two particular volcanic the landforms, that is Hunga Tonga and Hunga Hapai. Now, in the month of December 2021 to January 2022, 15th of January was when that final eruption took place. But from the month of December 2021, some amount of eruption was happening, which was emptying the magma chamber. Now, again, on 15th of, when we talk about, just a moment. So, as a consequence of that, you had basically the presence of two peaks, that is Hunga Tonga and Hunga Hapai. Now, the final eruption which took place in January 2022, that meant the emptying of the magma chamber, and that was the explosive eruption that I'm talking about. Now, as a consequence of that, both these individual landforms, they were basically subsumed. Much of that landform was destroyed, much of that was consumed by the sea, and sea water basically entered into that area. And this region, by the way, the Tonga Islands, if ever you get an opportunity, basically, uh, I don't know how many of you are aware, I had put out a YouTube video on our YouTube channel as well about the Tonga eruption. If ever you want to explore that in further detail about the Tonga eruption, you can always visit our YouTube channel, that is Byju's IS. You can search Tonga eruption and you will get a detailed analysis along with the animation as well. So you can do that. Obviously, when it happened, that is the time I released the video for that. So at that point of time, seawater entered there. Now, from 2015 onwards, you had this eruption creating these landmarks and these islands in the region of Tonga. All of that was completely consumed by sea. And what you now have is a remnant area around the Tonga Islands. So that tells you about the creation of that process of caldera. Okay, and example of caldera, for example, in those of you living in the region of Haryana or in the region of Delhi, for example, uh, when you drive out to the southwestern portion of Delhi, to the area of between Haryana and Rajasthan, so near Pataudi, right? The Nawab of Pataudi, you would have heard about the Nawab of Pataudi at least. So as you move out of Manesar, you move into Pataudi. There you have some of the very ancient calderas, which are said to be the remnant of the Aravali formation at that point of time itself. Okay. Yes, Damdama Lake. Does the pink bacteria can help to understand life? This pink bacteria is formed from the celestial body? No. This pink bacteria, it is that pink bacteria, the pink coloration of the lunar lake that you talk about, it is because of the bacterial culture which is going on around here. Right. So that collision with the meteor happened long time back. Lunar lake got created long time back. So that pink bacteria which got created happened now. So why it is very important, it is considered to be a geoheritage site? It gives you an evidence about the minerals, the materials which would be present in the meteor as it underwent that collision. Okay, but nice string of thought, Priya. That is good. Now in India, by the way, you have two geoheritage sites. Are we aware? One is the Lonar Lake. Are we aware of the second geoheritage site that we have in India? Are we aware of that? You can take a guess if you want. No? Okay. So, across the coastline of Karnataka, in the coastal area of Karnataka, you have a larger district that is Udupi. You would have heard about it. Now, Udupi has got a very famous beach that is the Malpe Beach. Off the coastline of Malpe Beach, around a few minutes of ferry ride, it will take you to a small island that is St. Mary's Island. Right. I don't know how many of you have visited it. If not, you can visit that place. So, St. Mary's Island is also a geoheritage site in India. Now, the reason for that being declared as a geoheritage site is also very interesting because St. Mary's Island, the rock formation, there you will find, if you ever happen to venture into St. Mary's Island or simply search St. Mary's Island on Google as well, you'll find that the rocks, they indicate a very unique pattern. It is kind of a hexagonal, perpendicular shape that you will observe in the case of the rocks, right? It has got a linear formations in hexagonal. Now that is a kind of a, again, volcanic formation. But then, is that enough for that to be regarded as a kind of a geoheritage site? No. You find that kind of exact rock formation somewhere else in the world. And that gives you an idea about the drift of the continents. So the type of rocks, the pattern of rocks that you find in St. Mary's Island, the exact similar rock formation of exact same geological origin is also to be found in Madagascar, which gives us a kind of a relation of Madagascar with the western coast of India. That region is still present in the region of Madagascar. That region indicates a continuity of the landmass of how the land would have been as the drift was happening. Okay, so that is why St. Mary's Island is also geoheritage site. Okay, now then we come to another interesting concept, and that is the mantle plume. Okay, now here when we talk about these mantle plumes, basically, what are they? Plume. What do you understand by the term plume? You would have heard about the term plume earlier as well. What do you understand by the term plume here? So, any rising column of sorts, that is what is regarded as plume. You have plumes of smoke. You would have read in the English literature or newspaper also that the region witnessed rising plumes of smoke which rose many meters up from the surface. So, plume is a kind of a rising matter. Now, here, you have to understand that right at the time of the formation of the planet, there was significant amount of heat which was trapped in the interior. and that heat continues to remain trapped up till today. What is that heat referred to as? Are we aware? Residual heat. Good, Satyanarayan. So, in the interior, you have heat which is trapped. That is the residual heat. Heat trapped in the interior since the time of formation of planet. Okay, so that is the residual which is heat which is trapped, and that heat keeps on getting released from various different areas. Now understand this, that mankind's understanding of mantle plume is not very old. We got an idea about mantle plume as late as the 1970s, right? Which was further expanded as more research papers were filed during the 90s. We got better idea about, okay, where the mantle plumes could be generated from. So plume is generated in general where there's a lot of heat. Now, where do we get a lot of heat? We get a lot of heat either at the region of the Gutenberg discontinuity, which is at the region of the outer core and mantle. There, slowly and steadily, the core is losing its heat. So that heat, basically, it starts melting some portion of the mantle. Think about it. If suppose this is the crustal layer, this is the region of the mantle core boundary. This is what we also refer to as Gutenberg. I will repeat these so many times, Gutenberg, Lehman, etc. I hope that by the end of it, you are able to memorize it. So this is where you have the Gutenberg discontinuity. Right? So here, when we talk about the Gutenberg discontinuity, this is where you have the outer core. Okay. Now, it is not as if that uniformly that heat is being lost by the outer core. Generally, it will be lost from a certain point. Okay. Certain areas are where the heat will be lost from. So let's assume that the heat is being lost from this area. Huge amount of heat is being supplied. Now, what will it do to the mantle? Mantle, again, I would want you to recap the concept that we studied, where we likened the earth structure with that of a coconut, where the hard shell on the outside of the coconut that we see, that is the crust. The white fleshy portion of the coconut, that is considered to be the mantle. So mantle is also solid, but then can be deformed as well. So if, let's suppose, in the portion of the coconut itself, you try to remove or you try to compress the flesh of that, it will be replaced and some other flesh from that portion will take over that region. So that is where, if you heat that particular portion of mantle, due to the residual heat which is supplied, it will melt the portion of the mantle here immediately. Now the molten portion is in liquid. Liquid is lighter than the surrounding solid. So the natural tendency of liquid will be what? Will be to rise up. Always liquid will try to rise up. But nonetheless, this liquid is also supported by the supply of the residual heat, isn't it? That residual heat is being supplied to it. So what that residual heat does, through the molten portion, it starts melting the portion above it. That starts melting the portion above it, and the molten portions, they start to rise up in the form of a kind of a plume. It will have a kind of a bulb-like head on top of it as it tries to rise up. Okay. Here, as it tries to rise up, it will start melting the portions in this region. Now, this is basically the molten area, right? Meanwhile, the solid portions from nearby will replace this. They will also get molten. They will also start rising up. So, as they continue to rise up in the form of these bulb-like structure with a broader head, they can virtually fill up any magma chamber which is present. Let's suppose there is a magma chamber present here. They can create a magma chamber by themselves. That is the amount of molten materials that they will carry. And they will lead to the creation of volcanic eruptions in many of the cases. Sometimes what they will also do, that these mantle plume will be able to generate a kind of a convection current. And whenever that convection current is generated, we observe that there is plate movement, that you have divergence of plate in certain cases where the plates will suddenly move apart. That means in some area, the plates are being pushed into each other. That is, convergence is also happening, right? So these mantle plumes basically are lot of heat which is supplied, the residual heat which is supplied from the interior. Just to give you an artistic recreation, this is your Gutenberg discontinuity. This is what you regard as the Gutenberg discontinuity. And it supplies that heat, and that heat traverses upwards, it moves upwards, and then basically observe it will travel in the kind of a bulb-like fashion here, right? Now, that can give rise to convective currents as well. It can fill up the magma chamber to lead to a kind of an endless and a continuous volcanicity, where the volcanic activities can be observed for hundreds of millions of years, right? For tens of millions of years in the same region, volcanic activity is being observed again and again and again and again. In the same area, volcanic events are happening. Regardless of the plate movement, in the same region, more volcanic events are happening because it is supported by the mantle plume. Okay, so for a long period of time from the 70s onwards, it was understood that the mantle plume is being supplied because of the heat of or the residual heat provided from the outer core. But then lately, researchers have also indicated that you also have the presence of a shorter mantle plume. A shorter mantle plume which can get generated from the region of asthenosphere. Why? Because of high amount of heat produced in the asthenosphere. And why is it that heat is produced in the asthenosphere? Because of thermonuclear reaction taking place due to the presence of radioactive materials in the region. So that is also going to lead to a kind of a volcanic eruption in the process, right? So let me write it down as well. So mantle plume. So before that, the definition, it is the convection of magma in narrow columns in upward direction from the core mantle boundary, forming a mushroom-shaped cap to the plume. Mantle plume magma is hotter than the surrounding magma because residual heat is getting provided, so it rises. Position of the mantle plume is considered to be fixed, where it remains in the same region for millions of years. Where it remains in the same area, same position for millions of years. Findings have indicated that sometimes excessive heat produced in asthenosphere asthenosphere can also generate a plume in upper mantle. Okay, they can sometimes also generate, but this is not very frequent. This is very rare. This is very rare. Okay, so mantle plumes basically can bring about changes. So when we talk about mantle plumes, first of all, can give rise, can fill up magma chamber and create continuous volcanicity events. When we say continuous, doesn't mean continuously magma or lava is coming out, but over a long period of time spanning across millions of years from the same region, volcanic eruption is happening. We have such regions across the planet Earth as well. We will talk about those areas as well. Now, other thing that it can do is can initiate convective currents in the mantle, which can lead to plate movements. Which plate movements? Divergent, in certain areas convergent, etc. Okay, so that is what the role played by mantle plumes. Now, as I told you, that can lead to, by the way, when we talk about that release of residual heat, so it can also happen. For a brief moment, I want you to open up your mind. Open up your mind to various different possibilities. Don't restrict yourself to the definitions that are written here on the PPT. Because here, when we talk about it for the bookish purposes, for the exam purposes, it is okay to consider that position of the mantle plume is fixed. But open up your mind to the possibility. When we talk about planet Earth and the age of planet Earth, the age of planet Earth is around 4.5 billion years, isn't it? Almost. The solid structure of the planet that we see it today, the shape of the continents and the oceans might be different. The forms of the landmass, etc., the extent of the land masses might be different. But the structure has largely remained consistent for almost 3 billion years now in terms of the structure and the layering of the planet. Now, here, it can be possible that here some amount of heat is released, residual heat. It generates a kind of a mantle plume, right? But it can also be possible that, let's suppose, 500 million years into the future, you can also have a kind of a situation where this heat is not produced from this region anymore, where you will find that maybe some residual heat can be generated from here as well. Isn't it? Again, maybe after 100 million years, after 500 million years, maybe another residual heat is generated from here as well. Isn't it? So when you consider these mantle plumes with the time scale of the history of the planet, they can be moving. But when you consider the position of the mantle plumes with the time scale of our own, that is human existence, they will always be fixed. They will never be able to move within the time span that we talk about the human existence itself. Because humans, we have been in existence in the present form for the past few thousand years, maybe 100,000 years or more, not more than that. Mantle plumes, when we talk about, we are talking about release of heat for 20 million, 30 million, 100 million years, or so on. So that is why, when considered on a geological time scale of the entirety of the planet, it can be considered to be moving. But when considered across the time scale of we humans, mantle plume is always fixed in one place. Is that understood? Is the concept of mantle plume understood? Pavni, sir, it's in PYQ. Define mantle plume and explain its role in plate tectonics. So, Pavni, can you now, or would you now be able to answer that question? Can it be viewed as a hot bubble of magma rising? Yes. Priya, is it same as a solar flare? No, not at all. Now, remember I told you that these mantle plumes can lead to filling up of the magma chamber and can basically lead to continuous volcanicity. Now, those areas which tend to lie above the mantle plume, where you have this continuous volcanicity that is occurring, those are referred to as volcanic hotspots. Right? When you hear about the term hotspots, the first thing that should come to your mind is any area where there is a frequent event repeating itself with a greater frequency, which is happening again and again. So, a hotspot is a volcanic area on Earth that exists over a mantle plume. Right? In this case, what happens? This mantle plume continuously continuously fills the magma chamber. It continues to fill the magma chamber. As the magma chamber continues to be filled, so you have volcanic eruption, volcanic eruption in the same region. As you have continuous volcanic eruption in the same region, means what? In that area, the plate movement will happen. Nonetheless, the plate movement is going to happen, regardless of whether there is volcanic eruption periodically or continuously. Volcanic eruption, the magma is present, magma chamber is generally present in the region around asthenosphere, immediately below the lithospheric plates, or at the margin of the crustal portion. So the plate movements will happen. So due to the plate movement, it kind of creates a series of volcanic landforms. So due to the simultaneous plate movements, a series of volcanic landforms are created. How? So let us understand that. Even though this image is also self-explanatory, where basically you observe that this is the region of the volcanic hotspot, and above it you have the tectonic plate which is moving. So here, think about it. Let's suppose you have the plate in this area. Okay, let's assume it. And here you have the magma chamber. In the entirety of the portion of earthquakes, volcanoes, or in fact, think about the geomorphology portion itself. This is one of the final key conceptual areas where you have to apply some. There will be in the next module also slight areas, but then this is one of the most important in terms of examination. So please try to gather all the attention that you can, put it here, Once you understand that, then a lot of portion, because questions have been asked in the mains, both for the optional as well as general studies, they have been repeated multiple times about these volcanic hotspots. In fact, one of the volcanic hotspots of the planet that is also responsible for the creation of large Deccan traps, the black soil region of India, that has been created due to a volcanic hotspot as well. Okay, so here let's suppose you have the magma chamber, which is continuously being supplied the molten materials from the mantle plume. Okay, now here this material, it emerges out through the vent and it creates a volcanic landform, let's suppose. Now, this volcanic landform creation takes place over a period of hundreds of years or maybe thousands of years. Then, nonetheless, this plate is in continuous motion, as the plates generally indicate a kind of a motion. So this plate is also in a continuous motion. So that means, let's suppose, when we talk about 5 million years from now. So 5 million years from now, this particular landform would have moved. It would have moved maybe here, right? Maybe it would still have the contact of the central duct, central vent to the original magma chamber. It might lead to an isolated volcanic event, maybe once or twice. After that, the duct gets blocked off, because then the magma will start erupting from the shorter source, from the shorter path. Another volcanic eruption happens, another landform gets created. Again, as it moves in the same direction, again the same process will be repeated, where you will observe that the earlier created landforms, they have been pushed to the side. So the earlier created landforms, they have been pushed to the side, and a newer volcanic landform erupts here. So this was the one which was created the earliest. This one was created after that. This one has been created recently. So just by taking a look at the shape of these landforms getting created, you can always get an idea about the direction in which the plate is moving over these hotspots. Example of these volcanic hotspots, when we talk about it, Reunion Islands. Where are Reunion Islands situated? Indian Ocean, Southern Indian Ocean. Right. It is, in fact, this Reunion Island. We consistently I have talked about the fact that Indian plate was moving at a very high speed. Indian plate was moving significantly from the southern hemisphere at a speed of 15 to 20 centimeter per year. You know, when Indian plate was above the Reunion Island, huge volcanic event and huge volcanic eruption occurred. Not because the Indian plate was on top of it, but because that was the scenario of planet Earth at that point of time. That was the phase when the oxygen in the ocean was completely depleted because of such huge amount of volcanic eruptions which was happening underwater almost everywhere in the interior of planet Earth. It was at that point of time, around 90 million years back, 95 million years back, when you had a series of volcanic eruptions creating many of the islands that you see in the Caribbean right now, many of the large sea mounts in the region of Caribbean islands. So, huge amount of volcanic eruption occurred that created the Deccan traps in India. But also, it was during this phase when you had lot of molten material which somehow found their way in the region between this area. That is the lithosphere and asthenosphere. Molten materials, they started basically accumulating there. And when the two portions, or when you think about the plates trying to move with respect to each other, if suddenly you have the molten portions which fill up the base, the movement gets accelerated in a way, isn't it? So the Reunion Island eruption was also responsible for accelerating the rate of movement of the Indian plate further northwards. Okay, not required for your general studies. This is just an additional information if you want to digest it. Then also Hawaiian Islands. Hawaiian Islands, where? In the Pacific Ocean. These are your examples of volcanic hotspots. If you take a look at the region of the Pacific, here observe, this is the present day portion of Hawaii. This is the Hawaiian island where you have the shield volcanoes. Now, this is where you have the large magma chamber, which is getting supported by the mantle plume. Now, here, if you observe the chain of volcanic eruptions, you'll find that even this series of volcanic eruptions which have occurred, they have been occurred because of the same magmatic material supplied from the same volcanic hotspot. So that means for a long period of time, at some point of time in history, this particular portion would have lied here. Okay, it is because of plate movement that that portion moved. So initially the Pacific plate would have moved like this northwards, and then they would have started moving eastwards. That is why here you'll find the Midway Islands. So you will observe the eruption occurring here 27 million years ago. The Suiku Islands, the eruption occurred 65 million years ago. It is these Midway Islands which were very, very important during the Second World War. It was, in fact, the Battle of the Midway, which is supposed to have reverted the trend of the Second World War. It is in these Midway Islands where the Americans, they managed to decipher the Japanese code and basically defeated the Japanese and sunk 4 of their aircraft carriers in the process. So that turned the tide in the Second World War as far as the War of the Pacific is concerned. But nonetheless, here if you will observe that the oldest volcanoes, so this indicates the direction of the plate movement. This gives you an idea about what is the direction of the plate movement. So this is your oldest eruption, and this is the newest eruption which is taking place. Okay, so these are your major hotspots. Is that clear? Is that understood? How eastward? Right, westward movement, Karan. Apologies for that. It is the westward movement that I was referring to. Is that understood now, Karan? Or is there a doubt? Good. So that is basically about the entirety of the volcanic eruptions. So then we come to certain other types and the other forms associated areas important for your examination. That is your intrusive volcanic landforms. This is largely going to be asked, and its importance is restricted to the prelims. Now, when we say intrusive, what do we mean? We basically refer to the fact that when you have magma which solidifies in the interior itself, right, without erupting from the exterior, it solidifies in the interior itself. That is what forms the intrusive landform, right? So what happens when we talk about the earth structure here? If this is the crustal layer, right, now, okay, okay, there's a lot of sound background noise which is coming. So let's do one thing. Let's take the break and let's combine it with the snacks break. So let's take a break right now. We'll come back after the break and we'll continue. So we'll continue at 6 p.m. Okay. We'll try to get rid of the sound midway in the meanwhile. Okay.